This should be easy enough. Speed is a scalar, just a number, and velocity is a vector, which is a speed and a direction. Another question about vectors and scalars, pretty straightforward. I think you know this. Answer is A. Okay, we're studying uniform circular motion. That means something's moving in a perfect circle at a constant speed. So in all cases of uniform circular motion, well, whenever anything is moving in a circle or a curved path, the direction at any instant is always tangent to the path, so that's important. If it's moving in a perfect circle, then the force and the acceleration have to be perpendicular to the velocity. And the way you should understand that is if the force is in the direction of the velocity, it speeds up. If the force is opposite the velocity, it slows down. If the force is perpendicular, then there's no component, only when it's perfectly perpendicular is there no component in the direction or opposite the direction of the velocity. So it has no effect on the velocity. So the speed changes, only the direction of the velocity vector changes. And that, because it's changing, it is an acceleration called centripetal acceleration. That's the central concept that we're learning in this set of exercises. So the answer here is A. Here's the question we just answered previously, so we can skip this one. Since velocity is a vector, it's changing direction, then that is an acceleration. Okay, we know the velocity vector is tangent to the circle. So vector E is that direction. It's not asking us, but if it asks for the acceleration or the force vector, it would be along G. That question will come up later. For the same reason, you can see that the answer to this one is D. We saw this one earlier. The answer is B, vector scalar. So speed is distance over time, and for a object moving at a constant speed in a circle, the circumference of the circle will be the distance in what's called the period. We use a capital T because it's a special time for one cycle or one circle. So you can use that information to calculate these velocities. Do that and then come back. Actually, when I went to do it, I realized there's a shortcut since they all have 2 pi in them. That's constant throughout. We could just do the R over the T, and I get these numbers. But if you wanted to actually get the velocity, just multiply that by the 2 pi. And then if you want a number, you just have to multiply the pi out. But you see how, since we're just ranking them, all we needed was these numbers, and we could come up with the ranking doing a lot less work. Since each of these is going to complete a circle in the same amount of time, the one that makes the biggest circle is going to travel the most distance in the same amount of time. Clearly A on the outside is going to be moving much faster than all the others, so the greatest speed is going to be A. As we discussed previously, an object moving in a circle at any instant, its direction is tangent to the circle. And since it's being bent and not speeding up, the velocity and the acceleration vector always point toward the center of the circle. And since the tangent and the radius vector are perpendicular to each other, they're always perpendicular to each other. So the velocity vector will be b, and the other two will be c. So the key word here is must, and the must statement means you have to reject all the answers except for F. The force and the acceleration vectors are always in the same direction. But the force can be in any direction relative to the velocity. Same direction, opposite direction, perpendicular. So the correct statements here are going to be C and A. Following what we talked about earlier, you should see that the answers are, you can see the answers I selected. Just check to understand why they're correct. So use this equation that gives us what the centripetal acceleration depends on. And so that would lead us to increased velocity would increase the acceleration as r is constant, and decreasing r would increase the acceleration if v is held constant, and the mass only affects the force. So increasing the mass, if we keep these things constant, then the acceleration doesn't change. Acceleration is a change in velocity of any type. So in this case, it's change in the velocity's direction. So that's D. So here we're asked about force and an increase in force. So an increase in mass, or an increase in velocity, or a decrease in radius will result in an increase in force. So those should be our three choices. Note, when an object moves in a circle, not only is the velocity vector changing, but so is the acceleration vector. It's not in one direction. It's always what? Inward toward the center of the circle. Both the acceleration and the force always point toward the center. And as we said in the last question, both the force and the acceleration are always toward the center. So if you look over all 5 statements, you'll see that the only correct one is E. Once again, an object, if the string breaks, the object's going to move tangent to the circle. So that's E again. Read through all the statements, and I think you'll conclude that the only correct answer is C. Read through the selections. The answer again is C. The passenger has a natural tendency to move tangent to the circle. The car turns. The passenger wants to go straight. The car pushes the person toward the center, and because the car is pushing the person toward the center, they have the illusion that they're being pushed out against the door. The object will lose contact at ring A and go in a straight line tangent to the circle. So it's false. If you read all the answers, you can conclude that the correct one is B. And similar to all the others, the natural tendency is to move in a straight line at a constant speed. It takes a constant inward force to keep the eraser moving in a circle. So we're on CG4. And we know from previous exercises that the velocity vector is always in the direction tangent to the circle. And the force and acceleration vectors have to be perpendicular to that and pointing toward the center. So there are our answers. Okay, this one deserves some explanation. So the first thing I'm going to ask you to do is draw a free body diagram of the roller coaster and then come back. Okay, this is what the diagram should look like. The force of gravity is down. And you say, well, isn't the thing going to fall? Yes, if the thing were stationary, there would be no normal force. It wouldn't be pressed against the track, and it would just fall. If the thing went slow, it wouldn't make it to the top. It would fall. But if it's going fast enough to make it around, then the gravity force is helping to keep it in the circle, but the track will also push down. So the normal force has to be normal to the surface. So there's two forces acting, but how big the normal force is will depend on what? How fast it goes around. So if it doesn't go around too fast, the normal force may be small. If it goes around very fast, the normal force will have to get bigger in order for it to keep the track in a circle. So try and understand that physically. Okay, now with that information, go ahead and answer the questions and see what selections you come up with. Okay, so if you understood what I said, you'll realize that the normal force could be smaller than gravity or bigger than gravity. It depends on the acceleration, how fast the cart is going around the track. And the normal force has to be normal to the surface, and so it has to be directed downward. So E and G. Okay, draw the free body diagram of this one, and then I'll explain how to understand this one. So here's the diagram so we can picture it, and then here's the free body diagram. And if you got this right, you should congratulate yourself because it's not easy. So obviously there's a force of gravity. You should have that. But what keeps the person from sliding? Since the surface is perpendicular, it has to be a friction force, right, that keeps the person from sliding down. And the normal force, right, is always normal or perpendicular to the surface. So given this free body diagram, answer the question and see what you come up with. So yes, the centripetal force is the force that keeps the person moving in the circle is the normal force. Okay, there's the diagram of the situation, a string and an object going in a horizontal circle. Draw the free body diagram of the object, the eraser. So that's what your free body diagram should look like. There's the force of gravity going down, and there's the tension force at an angle. Now notice the tension force is going to have a component that's horizontal and a component that's vertical. And the reason it has to have a vertical component is because that has to be equal to the force of gravity, because there is no acceleration this way. The only acceleration is in the horizontal plane. And so it's a component of the tension force actually that's causing the centripetal force, but it's just asking which force. It's going to be the tension force. So that's F. So this is like the plane at the bottom of its path. As this goes back up, it's moving in a circle. The normal force will be directed upwards, and it has to be bigger than the force of gravity, because if it were sitting still, they'd be equal, but since it's moving in a circle, there has to be a net force toward the center of the circle. So the normal force is directed mostly upward. B, and it has to be greater magnitude F than the force of gravity. So think about this one. If you move too slow, the bucket's going to fall. If you move fast, there'll be tension in the rope, and the faster you move, the more tension in the rope, because you'll need more pulling down force to keep the thing moving in a circle. But if you slow down just to the point where you just make the circle without it falling, in that case, the tension force can be zero. In the case where the acceleration decreased to exactly the value of gravitational acceleration. So the answer for this one will be B. This is a little tricky. Think about it. See if you can convince yourself that the tension force, the faster you go, the bigger the tension force is. And as you slow down, just when there's still enough speed that it's not going to fall, that's where the tension force goes to zero. B. So here's the one we got wrong last time because I only guessed one answer. And in this case, we know C of greater magnitude, because there has to be a net force up, and it's going to be directed upward, E. Okay, here we are, CG5. Now we have some calculations. So read through this and see, do as much as you can before you watch me do it. Okay, so first I did FG, or F grav. That's just mg, and that's what I got. And then I get the net force. Notice they call it F net. I write it this way, so they mean the same thing. You should understand that. And that's just m times a. Oh no, wait a minute. I got to get a first. So v squared over r. So we have the v and we have the r. So you square that, divided by r. And I got that. And then once I have the acceleration, I can multiply it by the mass and get the net force. And then the last thing I get is the tension force, because the tension force minus that has to be equal to the net force. So you've got to add. Let me show you how that's written out. So that's how it looks if you write it out. The sum of the forces are Ft minus Fg equals ma. And so Ft is Fg plus ma. And that makes sense, right? Because the net force is this. So in order, and so you have to add the 32, and you get that. So if you take the tension force and you subtract gravity, you get your net force. So just make sure you understand all that. You're not just doing calculations without thinking. Let's hope those results are correct. Okay, here's another one. So notice the difference here. In this case, both forces are down. So just so we don't have all negative signs, we're going to say that down is positive. So the tension force is down, gravity force is down, they're in the same direction, they're positive, and the acceleration's down. So I'm just going to leave them all positive. And that means to get the tension force, in this case, you're going to have to subtract the gravity force to get the tension force. Because the sum, you'll see when you do the calculation, and the acceleration is calculated the same way. So do that. So think about this, so you're just not blindly doing calculations. The mass times g gives you the force of gravity. And the acceleration is calculated by v squared over r, and then the net force will be the mass times the acceleration. So multiply the acceleration by the mass and you get the net force. But now we have to get the force of tension, you subtract the force of gravity, right? Because gravity and tension are both down, so gravity plus tension has to equal the net force. Make sure you understand that. Okay, let's check the numbers. Okay, it does take a little time to do that, so that's just mg, and there's no acceleration this way, so these two forces, the sum of the forces in the y direction would be 0, so the normal force in this case has to be equal to the gravity force. And then we calculate the acceleration, v squared over r, and I get that. And if I multiply the acceleration times the mass, I get the net force. And the net force and the friction force is the only force, so those will be equal. Okay, same routine. Get F grav first, 421 times 9.8. Then get the acceleration, v squared over r. And then multiply the acceleration times the mass to get the net force. That. And so the net force is, notice the acceleration's down and F grav is down, so this is in the opposite direction. So you're subtracting the F norm from the F grav to get that, the MAY. And so the F norm is the difference in these two numbers. If I bring this F norm is going to be FG minus MA. So FG minus MA is that. That's F norm. Okay, same thing. F grav, mass times g, acceleration, v squared over r. Notice this is the diameter. In fact, when I did it, I used 192, and I knew I had the wrong number because the acceleration was less than 9.8. And if the acceleration, the centripetal acceleration, were less than 1.98, the pilot would fall off the seat. So anyway, yes, that's the diameter, so the radius is 96. And that gives you that acceleration, which is greater than 9.8. So a normal force, gravity force plus the normal force, gives us the net force, the mass of the pilot times g. So those two have to add up to that. So I took this, subtracted that to get the normal force. Just think that through so you understand it and you're not just doing the math, because it would be easy to add when you should be subtracting and vice versa. Okay, let's check. Hope all those calculations are right. Whoops, something was wrong. Let me see if I can go back and find it. Okay, I went back and looked and saw that I had 511.7 rather than 511.5, so it seems like there was just some minor calculation error. Anyway, the method was correct. So now let's do this one. Okay, a lot of calculations here. So take the mass, multiply by g, get the gravity force. The y force has to be equal and opposite. There's no acceleration this way, only this way. And to get the acceleration, we need the velocity. So the radius, the circumference of the circle, 2 pi times r, divided by the time for one cycle or one rotation. That's 10, so the t is going to be 0.921 seconds. And that should give you that for a velocity. You can check my numbers. And if we square that and divide by r, should get that. And then if we multiply that times the mass, we should get that. And the net force and the Fx, the x component of the tension force, have to be the same because that's the only force acting toward the center. Okay, let's hope those numbers are all correct. Okay, let's go through this one. So we have m times g, that's F grav. And what keeps the person from falling is the friction force. So those two have to be equal and opposite. And the force of the wall pushing the person toward the center, the normal force, is the centripetal force. So first we get V, 2 pi, that's the diameter, so it's going to be 2.34 times 2 pi divided by the period, 2.08 seconds. That's what I got. Then I squared that and divide it by 2.34, the radius of the circle. And I got that. Now notice, this is more than twice g. So the feeling, think about the physics, the feeling of this person lying on the floor, they would feel their weight. The feeling of the wall pushing on them is double their weight. In other words, if there were a scale there, it would read more than twice the person's weight. That's why the normal force is so big. So try and understand that physically, actually, the feeling of your body if you've ever done this ride. Anyway, let's hope all those multiple calculations are correct. Good. Okay, we'll see that we saw this one before, but I'll redo it. So we've got the m times g. That's the weight of the pilot. And the velocity squared divided by 82 meters. That's the diameter, right? Gives us that for an acceleration. And the acceleration times the mass gives us the net force. And notice the net force is more than 3 times the weight of the person, because the acceleration's more than 3 times 9.8. And so the net force is going to be the normal force minus this. So we have to add that to this to get the normal force, right? The normal force minus grav is the net force. So the person sitting on the seat is actually experiencing a force that's more than 4 times what they would feel if they were just sitting on the seat. So when this kind of loop-the-loop happens, it puts a lot of stress on the pilots, right? Sometimes they pass out. That's the physics. Okay, let's see if the numbers are all correct. Good. And the final one is the reverse of what we just did. And I did one of these earlier, but let me just put the numbers in so we can get our success. Okay, look at the difference here. This is interesting, right? We get the same F grav because we get the same mass of the pilot. And we're going slower, so the acceleration's quite a bit less. In fact, it's just slightly more than g. It has to be more than g, otherwise the pilot would fall. But it's just slightly more than g. So the gravity force, the net force is this, but the net force is the sum of these two. So this plus this equals that, so I subtracted that, and I get a force of 133. So in this case, the pilot is experiencing a normal force, which is only, about 1/3 or 1/4 their weight. They're feeling very light on the seat. So you can imagine going over the top. As you go slower and slower, you're going to get to the point where you're going to begin to fall off the seat. You won't be pressing against the seat at all. So anyway, try to imagine that and understand the physics that we're doing the calculations for. Okay, final check. And now I'll put in the table of contents. There we are. That's where the major sections are in the video. Hope that helps.